We'll begin by looking at what happens if we want to find the derivative of data that we've collected from an experiment using our numerical differentiation techniques. So the first thing we want to remember, at least for the techniques that I will be discussing in this lecture, is that however the data was collected, it has to be uniformly sampled. So again, everything, usually it's going to be based in time, but everything had to be collected every 100th of a second, every second, something like that. We can't have some every other second, and some data being collected every 1 second, and some being collected faster. That's not going to work for these techniques. We need that constant step size in order to use our numerical techniques. Now there are other methods that don't need a uniform step size that get a little bit more complicated. I'm not going to address that in this lecture, but if you are interested, those techniques are available. Now there's other ways you could get around this if you resample all of your data using something like interpolation, but then it starts to get hairy when we want to do numerical differentiation because we're making some estimates at what those values are rather than having the actual data. Now we see when we collect data is kind of the general rule of thumb is the faster we can sample our data, so the less time between data points that we're collecting, the better. If we have a low sample rate, our differentiation is not going to be very accurate, whereas if we increase our sampling rate, it can increase the accuracy of our estimate as to what the derivative is. This is similar to problems we saw with what we called aliasing, where we didn't sample our function fast enough, so if we tried to recreate it, it didn't look at all like what the original sample was. So usually our rule of thumb is sample as fast as you can to get the best results possible. When we're doing differentiation of our raw data, it's very susceptible to noise in the data. So what that means is we could have some sort of measurement noise, some sort of observation noise, where maybe, say we're monitoring a voltage and it's supposed to be 5 volts, we're reading a little bit more or a little bit less than 5 volts. If we sample again, it could be a little bit higher or a little bit lower than what the actual value is going to be. So this is what we call noise in our data. And all experimental data is going to have noise in it. It could have a little bit of noise, it could have a lot of noise, depending on our equipment. And actually here, if we're just using a lower accuracy method, a higher sampling rate with noise can actually make the problem even worse. But we can use higher accuracy methods in order to repair this. And also what we might want to do is filter our data first, which basically smooths out some of this noise. And that's a topic for follow-up courses to this. Again, if you use a low accuracy method, it might not work as well. If you start increasing your accuracy, meaning you're using more and more points in your differentiation, that can start to mitigate the effect of some of this noise. And what we'll see in later examples is that even though differentiation is affected by this noise, integration of our raw data is actually not, since integration is kind of going to add together some of the overestimates and some of the underestimates and then negate the effect of this noise more or less.